Good afternoon, everyone, and a very warm welcome to you all to the second of our 3 online lunchtime seminars to outline the science on ammonia, which will help inform future policy. Many thanks for joining us. My name is Alistair Carson. I'm pleased to be chairing the series of webinars this week in my role as Director of Science, Evidence and Innovation Policy Division in DARA. Good afternoon to Paddy Savage, Head of Ammonia Policy Branch. Good afternoon, Paddy.
Good afternoon, Alistair. Thank you.
Paddy's joining me on the panel to coordinate the Q&A session, and our 2 presenters, John McElroy and Erin Sherry, both from the Agri-Food and Biosciences Institute, are on our panel, and I'll introduce Erin and John formally immediately prior to the presentations. Also joining us in the panel is Tom Misselbrook from Rothamsted Research in Devon. Good morning and welcome, Tom.
Hi, Alistair.
Tom is a co-author in both of today's presentations. Our presenters from Monday's webinar are also joining us this afternoon. Sarah McCucken. Good afternoon, Sarah. Sarah's on mute.
Afternoon.
I could assure you Sarah's there, Head of Natural Science within the Northern Ireland Environment Agency. And Keith Finnegan, a Principal Scientist within NIEA, will be joining us shortly. But before moving on to our presentations, small bit of housekeeping. Could I have just the housekeeping slide, please, just to run through. The seminar itself will run for 60 minutes through to 1 o'clock. We'll have a 5-minute Q&A session after each of our 2 presentations. We're really pleased with the level of engagement during Monday's webinar, with a series of wide-ranging questions submitted during and those were submitted through the Q&A function, and I'm sure today's presentations will initiate a similar level of interest. Where appropriate, we may need to group questions into topics for answer, and Paddy will collate those. And I can assure you that any questions which aren't reached in the time available will be responded to by email. The next slide just goes through the mechanics of asking a question from the panelists. It may vary slightly in terms of your own screen, but in terms of WebEx, if you click on the graphic with 3 horizontal dots in the first instance, and then click on the Q&A option within that icon, and finally enter your question in the box provided. And please ask questions and enter your questions as we go through the presentations, and we'll be able to then collate them and have a coordinated Q&A session. Today's presentations and today's WebEx seminar will be recorded and be made available. In fact, if you weren't able to join Monday's webinar, I can direct you to the DARA website where you'll find the link to the video for Monday's webinar. Okay, that's all in terms of housekeeping. On Monday's webinar, our presentations highlighted that ammonia is a particular issue for Northern Ireland agriculture, the cornerstone of our economy, due to the predominance of livestock farming. Ammonia, a form of nitrogen, is caused largely by the management of slurries, manures, and the spreading of fertiliser. 96% of ammonia emissions in Northern Ireland come from agriculture, damaging many of our most vulnerable natural habitats, as detailed on Monday's seminar by NIEA's Keith Finnegan. Ammonia isn't a unique challenge to Northern Ireland. Countries across the world are working hard to find solutions to what's a complex issue with no quick fix. However, there's a lot we can do together in Northern Ireland to reduce our emissions, whilst at the same time help our agriculture sector to become more efficient and sustainable in the longer term. Now, delivering on this challenge requires a high-quality evidence base, and this is a science which is the focus of the webinars this week. And in terms of that science, it's emission reduction modelling that we're going to turn to first this afternoon in a presentation from John McElroy on farm-level ammonia reduction case studies. John leads the Air Quality and Climate Change Research Programme within afbi's Agri-Environment branch, with a particular focus on the measurement and modelling of agricultural ammonia emissions and emission reduction strategies. John, we look forward to hearing your presentation this morning, and it's over to you. Thanks, John.
Alistair, well, thanks very much for the introduction, and thanks to everyone for tuning in this afternoon to the series of presentations. So the first of today's presentations really deals with farm-level case studies on ammonia reduction, which will hopefully give viewers a feel for some of the potential ammonia reductions that are achievable on typical Northern Ireland farms when proven ammonia reduction strategies are adopted on the farm. So next slide, please. The NARCES model is used as the UK's national ammonia inventory model, and this is applied at a UK-wide level, but it's actually equally applicable to conduct farm-scale ammonia emission modelling. So what we did was use the NARCES model to estimate ammonia emissions from dairy, beef, pig and poultry systems, which have sizes and management practices deemed to be representative of Northern Ireland livestock production systems. Now, the livestock systems scenarios that we developed were designed and based around, for example, survey and statistical review data. So, for example, the statistical review of Northern Ireland agriculture. We also used existing NARCES parameters and emission factors which are used within the model, as well as also expert advice from both afbi and CAFRE staff on typical Northern Ireland farm management practices. So then what we did was, to these scenarios, we applied a suite of ammonia reduction strategies to determine the potential reductions in ammonia that are achievable on those farms. Now, the reduction strategies that we applied were based around existing knowledge and proven technologies, which are both technically feasible, practical, and could also be reasonably adopted within roughly a 5 to 10 year time frame. Next slide, please. So focusing first on the dairy sector, I suppose two representative dairy systems had their ammonia emissions estimated here. Firstly, a grazing housing system, and secondly, a fully confined system where grass is cut and carried during the summer. Both scenarios were based on 100 cow herds with 30 replacements per year reared on the farm, and the herds were housed on solid floors with scrapers and outdoor slurry storage. In both scenarios, the slurry was spread by splash straight to grassland, and typical CAN and urea applications were also considered within the scenarios. So the only real difference here between the scenarios was actually the grazing period, which was set at 186 days for the grazing housing system, and milk yield, which was set at 7,220 litres for the grazing housing system and 8,500 litres for the fully confined system. And that's in consideration of the higher milk yields, which are typical of these total confinement systems. So to these baseline scenarios, 6 ammonia reduction measures were applied to evaluate the effects of the combined measures on ammonia emissions from the systems. So these ammonia mitigation measures were reducing the crude protein content of the whole diet from 18% to 16%, extending grazing from 186 days to 200 days, in other words, an additional 2 weeks of grazing. Now, of course, this was only applicable to the housing grazing scenario, not to the fully confined scenario. We also increased the housing scraping frequency to have this happen every 2 hours, and this has been shown to be the optimum scraping frequency to reduce ammonia emissions from housing floor surfaces. We also covered our outdoor slurry stores within our scenarios. Crucially, we moved from slurry spreading by splash bait to slurry spreading by trailing shoe, in both cases to grassland. And finally then, the final ammonia mitigation or ammonia reduction measure we applied was replacing straight urea with stabilised urea on the farm. Next slide, please. So let's look at the modelling results to see by how much the applied ammonia reduction strategies reduced farm emissions. So a total ammonia reduction of 43% was determined for both systems after the application of those 6 ammonia reduction strategies. The most significant reductions are achieved within housing, and that's due to the reduction in crude protein and increased scraping, as well as at slurry land spreading with that shift from splash plate spreading to spreading by trailing shoe. The reduction strategies outlined reduced ammonia emissions for the 100 cow grazing and housing herd, which is on the left-hand side of the graph here, from approximately 3.7 tonnes to 2.1 tonnes per annum. Fully housed systems, which we can see on the right-hand side here of the graph, have higher ammonia emissions associated with them. Emissions here were estimated at 5.9 tonnes for the 100 cow herd without the reduction strategies, and this dropped to 3.4 tonnes when the reduction strategies were applied. Now, notably, the application of the reduction strategies brings emissions from the fully confined system to below that for the baseline grazing housing system. Next slide, please. Now, the modelling results highlight that there is a significant difference in total emissions between the two dairy management systems which were modelled here, both of which have the same number of animals. And this is effectively due to full year housing in the confinement system, leading to all of the excreta being deposited in the house, with urine and faeces mixing readily and having to be subject to subsequent manure management, so storage of the slurry and obviously land spreading of the slurry. In the grazing housing system, a significant proportion of that excreta is deposited at pasture, and this actually incurs lower ammonia emissions because urine, which is the main source of the ammonia, infiltrates the soil and does not mix as readily with faeces as it would within housing. So under the parameters that we modelled here, for an identical herd size, fully confined systems were found to produce approximately 57% more ammonia per cow than grazing housing systems. However, considering that higher expected milk yield for fully confined systems, these systems produced approximately 33% more ammonia per litre of milk than the grazing housing equivalent. Next slide, please, Fatty. So moving on to the beef sector, as I'm sure we're aware, the beef sector in Northern Ireland is substantially more disaggregated than the dairy sector, and there are a variety of different husbandry systems within the wider sector. Now, whilst a range of different scenarios were modelled here, only 2 scenarios will be presented today, but hopefully these are relevant to a significant proportion of Northern Ireland beef production. So firstly, we modelled a 24-month steer dairy origin beef system, which had 22 finishers and 22 calves. This herd grazes for 192 days in the year. This housing system has slatted accommodation for the finishers and straw bedding for the calves. Slurry is stored under the house, and farmyard manure is stored in outdoor heaps. Slurry is, like with the dairy scenarios in the baseline, sprayed by splash plate, and approximately 1.5 tonnes of nitrogen fertiliser are applied per annum in this scenario, 260 kilo of which is urea. The second system modelled was an LFA Hills Suckler Cow Spring Calving system, and this system had 18 beef cows and 18 calves. Now, this herd grazes for a slightly shorter 180-day period, obviously reflecting the LFA conditions. Like with the previous scenario, this system is housed exclusively on slats with under-house slurry storage. Again, slurry is sprayed by splash plate, and there's no nitrogen fertiliser application in this system based on stocking rates and the predicted area farmed for this scenario. Now, in the absence of an emission factor in the UK inventory for slatted floors, which afbi are currently working on determining, the solid floor emission factor, which is applied in the national ammonia inventory, was applied to these systems for these scenarios. So to these 2 baseline scenarios, 5 ammonia reduction measures were then applied to evaluate the effect of the combined measures on ammonia emissions. So these mitigations were extending grazing by 2 weeks, installing a low emission housing floor system, such as, for example, slat mats, increasing the housing scraping frequency to every 2 hours, again the optimum scraping frequency, moving from slurry spreading by splash plate to slurry spreading by trailing shoe, and finally then replacing straight urea with stabilised urea. Of course, this was only applied to scenario 1, as scenario 2 did not have a nitrogen fertiliser application. Next slide, please. So looking now at by how much these applied ammonia reduction strategies reduced farm emissions, in the dairy origin beef scenario, a total ammonia reduction of 34% is achieved. The majority of those reductions are achieved in housing, and that's because of the novel flooring system and increased scraping, but also at land spreading with that move to trailing shoe. Reductions in emissions at nitrogen fertiliser application are also significant in the total farm reduction. Now, reductions in this scenario are in a way limited by the proportion of manure in this system as farmyard manure from the straw bedding, and this was modelled as being broadcast spread to grassland and without an emission reduction strategy applied. And that's unlike the slurry proportion of the manure from this system, from which emissions were reduced by that move from splash plate to trailing shoe. In the Hills Suckler Cow scenario, a total ammonia reduction of 42% is achieved. And again, the majority of reductions here are achieved in housing, where a 54% reduction over the baseline is achieved, and also at land spreading, where we see approximately a 57-58% reduction. over the baseline with that move to trailing shoe. Now, given the smaller scale nature of the beef sector in Northern Ireland compared with the dairy sector, it was deemed inappropriate to model a move really from under slat stores to, say, outdoor covered stores for the relatively small beef herds that were modelled. And likewise, a reduced crude protein diet wasn't modelled in these beef scenarios, although this is a possible reduction strategy within the sector. Next slide, please. So moving on to the pig sector in Northern Ireland, I suppose two systems generally represent a large proportion of Northern Ireland producers here. Firstly, a sows and litter system to 40 kilos, and secondly, a finishing pig system from 40 to 115 kilos. The sows and litter system was comprised of 250 sows and 1,125 weaners on a slatted floor slurry-based system with slurry spread to grassland by splash plate. The finishing pig system was comprised of 1,500 finishers managed on a similar slatted floor slurry-based system, and again with slurry spread by splash plate to grassland. So to the pig scenarios, 4 ammonia reduction measures were applied to evaluate the effects of the combined measures on ammonia. And these were improved animal genetics by means of a 5% improvement in the feed conversion ratio, which would result in an 11% reduction in nitrogen excretion from those animals, as well as that a reduction in the dietary crude protein from 17% to 15%, which would result in a further roughly 22% reduction in nitrogen excretion. And this was applied to scenario 2 only, so only to the finishers. Thirdly, then we modelled a move from under slat slurry storage to outdoor covered stores with frequent removal of slurry from the house to the outdoor store. And finally then, as with all the previous scenarios, as a crucial end of line technique, we modelled that move from splash plate spreading to spreading by trailing shoe. A 5th measure was actually also applied to a duplicate scenario 2 run, and this was an in-house slurry acidification system which adds sulfuric acid to the slurry in an outdoor covered reception tank and then recirculates this through the house in a slalom type system. Now, this is currently one of the most effective approaches in terms of ammonia abatement, as it significantly reduces not only housing and storage emissions, but also subsequent land spreading emissions. However, it's very difficult to retrofit this type of a system to existing facilities, and so it requires the bespoke engineering of the slurry storage infrastructure to accommodate this type of solution. Next slide, please. So looking at by how much the applied ammonia reduction strategies reduced farm emissions, in the sows and litter scenario, a total ammonia reduction of 45% was achieved. The majority of reductions here are achieved in housing due to the genetic improvement of the animal and also the frequent removal of slurry to a covered outdoor store. Actually, the move to covered slurry stores achieves proportionately more reductions in the pig sector than in the cattle sector, and this was when we modelled this at a national level, and that's due to the higher ammoniac and nitrogen content of the pig slurry compared with cattle slurry, and the fact that pig slurry does not crust as readily as cattle slurry, which often forms a crust which acts as a natural barrier to a proportion of the ammonia emission from the storage of that cattle slurry. Finally then, the land spreading emissions are also significantly reduced by approximately 59 or 60% with that move from splash plate to trailing shoe slurry spreading. In the finishing pig scenario, a total ammonia reduction of 55% is achieved, slightly higher, and the additional reductions here above the previous scenario are largely attributable to the reduction also that was applied here in dietary crude protein. When the in-house slurry acidification system, as you see on the far right-hand side of the graph, was applied to that scenario 2, a total farm ammonia reduction of 79% was achieved. Now, based on the Danish emission factors, we can expect an in-house slurry acidification system to achieve ammonia reductions of approximately 60% at housing and 64% at land spreading when acidified slurry spread by splash plate. Now, if that acidified slurry is land spread by trailing shoe, as was modelled in this scenario, we can expect ammonia reductions at land spreading of close to 90% compared with, say, standard slurry being spread by splash plate. So significant reductions to be achieved here under that final model scenario. Next slide, please. And finally then, focusing on the poultry sector, a range of typical Northern Ireland systems were modelled here, of which only 2 will be presented today due to time constraints. Firstly, a standard broiler system, and secondly, a multi-tier free-range layer system. So the standard broiler system consisted of 45,000 broilers in a mechanically ventilated litter system. Manure was stored in a litter heap and was broadcast to grassland. The multi-tier free-range layer system consisted of 16,000 layers in a multi-tier system with belt removal of litter. 20% of the layer time was modelled as being spent outdoors, and like with the previous scenario, manure was modelled as being stored in a heap and then broadcast to grassland. 3 ammonia reduction measures were then applied to both systems to look at the effects on the combined measures on ammonia emissions. So these were improved bird genetics, again by means of a 5% improvement in the feed conversion ratio, which would result in a 12% reduction in nitrogen excretion. Secondly then, a 1% reduction in dietary crude protein, which would result in a further 10% reduction in nitrogen excretion. And thirdly, key mitigation within housing was that of litter drying to increase the litter dry matter beyond that in the applied housing emission factor. And this gives us a 30% reduction in the housing emission factor. Next slide, please. So in terms of the effect on poultry farm emissions, both scenarios achieved a 24% reduction in total ammonia emissions when the quoted reduction strategies were applied. The majority of emissions reductions are achieved in housing, where we see a 45% reduction here, and that's due to the model genetic improvement, the reduced crude protein of the diet, and the increased litter dry matter in combination. However, these strategies actually also reduce emissions of land spreading, as lower nitrogen excretion leads to manure with a lower ammoniacal nitrogen content, which also results in lower emissions when land spread. Now, manure land spreading emissions are a significant proportion of total emissions from a poultry system. This modelling exercise assumed manure land spreading emissions as part of the whole modelled poultry system. Now, the reality is that in Northern Ireland, a large proportion of poultry manure will be exported off the farm, so land spreading emissions may not be a component of the local system as such. So if we were to emit land spreading emissions from these scenarios, ammonia reductions in and around 35% are achievable across all of the scenarios. Now, ammonia reductions during the land spreading of poultry litter to grassland are inherently difficult to achieve. Now, we can incorporate poultry manure, for example, into tilled land within 24 hours to give us significant reductions over broadcast spreading in grassland, but this wasn't modelled here, as application to grassland is seen as the more common practice in Northern Ireland. Another reduction option possibly would be to spread under favourable wet weather conditions. So, for example, under cooler conditions, we can reduce our ammonia emissions when compared with, say, spreading under hot summer conditions. Or another example would be to treat litter in the house or storage with alum or aluminium sulfate. And this has gained popularity in the United States and as a form of acidification can achieve emission reductions of up to 70%. Earth scrubbers also offer significant reduction potential, up to 90% reduction of housing emissions for both pig and poultry facilities, but weren't modelled as these are seen as cost prohibitive. And just to briefly summarise, final slide please. So as we've seen, significant reductions in farm ammonia are achievable across the 4 sectors. The reduction strategies we modelled here were chosen to serve as examples of sector relevant proven reduction measures and are by no means prescriptive. Indeed, there are a range of other equally valid reduction strategies which weren't modelled. Now, whilst only 9 scenarios were presented today, a total of 16 were modelled across the 4 scenarios presented, which we are planning to publish in due course. So this concludes the presentation, and I'm happy to take any relevant questions now.
Thanks very much, John, for a very comprehensive paper. And I would also like just to welcome onto the panel Uli Dragosits from the UK Centre of Ecology and Hydrology, who's joining us on the panel this afternoon. Paddy, with some interesting questions coming through there, maybe you could collate and relay the first question there, please.
Yeah, absolutely. So the first question we have in, John, is this is a pretty simple one, but just how are the ammonia emissions measured in all of these scenarios? So I suppose just take through, exactly what happens and how you've come up with these reduction figures.
Yeah. So in this case, this is a modelling exercise. We used the NARCES model, the National Inventory Model, to model emissions. So we didn't actually measure emissions in this case. What we're actually doing is using the national inventory, using the emission factors within the national inventory. The emission factors are based around scientific research into typical farm management practices, be it certain types of livestock housing systems, certain ways through which slurry is stored, or certain slurry land spreading types of systems, which have emission factors associated with them, estimates of emissions from those systems. And we have then used that with the parameters which I presented, the livestock numbers and the systems through which the livestock are managed under typical Northern Ireland livestock management practices to give us estimates of ammonia emissions from those systems. So we didn't actually measure ammonia, we modelled ammonia.
Okay, thank you, John. And then the next one I have here is, can you identify the benefits of trailing shoe versus splash plate slurry spreading? And then can I maybe just add to that myself, then also maybe a comment as well on trailing hose?
Yes, so in terms of the reduction factors that are applied within the national inventory, the baseline emission factor for splash plate is applied a reduction factor of 30% for dribble bar or trailing hose and a 60% reduction for trailing shoe. There are also reduction factors in the national inventory for injection spreading, whether it's shallow injection or deep injection, which give you greater emissions of 70 to 80% over splash plate. So those are the emission factors applied in the national inventory, and those emission factors are based on a large body of scientific evidence into those spreading practices.
Okay, thanks, John. And then there's the next question. Maybe some of the other panel members may wish to comment, but I suppose it's how can the reductions that are identified by some of these measures be reflected in the planning system? Now, I know that's probably beyond the bounds of your research, John.
Yeah, I mean, happy to pass it over to a policy person if you want to try to answer that.
Hey, Paddy, it's Keith Finnegan here. Maybe I could try to take that one.
Yep.
Well, as everybody knows, the protocol that MEA uses for assessing plans and projects has been under review for some time. A revised protocol for assessing projects will form part of the ammonia strategy consultation, which the department hopes to issue in the coming months or shortly. And as part of that, we'll be taking views on how best emission reduction can be implemented. But the protocol is going to be future-proofed in that when emission reductions are realised under the ammonia reduction strategy, they'll be taken into account in the assessments of plans and projects.
Okay, thank you for that one, Keith. And then there's just, John, there's a few questions that have come up here on acidification, and as well there's a range of comments made. Does it apply to cattle? Are there any consequences to it? And the impact on soil conditions. So, if you maybe just want to take that one.
Yeah, I mean, it's equally applicable to cattle slurry as it is to pig slurry. It's maybe more common in the pig sector, for example, like Denmark and Germany. But the companies that offer these systems also offer them for dairy systems. I mean, there's an extensive body of research really into acidification, and it is proven to achieve significant reductions of up to 80%. One of the issues that has been raised often is in Northern Ireland specifically, and with our clay soils and our high rainfall, the fact that we already have high soil acidity, and that this suboptimal pH can of course reduce grass yields, that applying acidified slurry would require obviously additional liming to offset that reduced pH of the slurry. But we've very briefly worked out in terms of the quantities. So effectively, as a rule of thumb, approximately 1 kilo of lime would be required to offset the addition of roughly 1 litre of sulfuric acid. So this would equate to approximately 240 kilos of additional lime per hectare every 4 years. So this isn't a significant amount of extra lime, as the lime application rates say are in the region of 4 to 5 tonnes per hectare every 4 years. But we also need to consider, as well as just the effect on soil pH, we need to look at wider soil health issues, such as the effects on the mycorrhizal fungi in the soil, earthworm activity, soil enzymes, for example, all of which are fundamental for a healthy soil. So we hope to explore these research issues, through research in the near future.
Okay, and just one very quick final question, John, as we're just at the edge of time, but if all ruminant livestock farmers extended the grazing season by 2 weeks each year, how much would that reduce emissions by?
So that's more of a national scale question, I take it, than a farm scale.
I think so, yeah.
I'm trying to remember, thinking back to the national modelling that we did, Paddy, this is off the top of my head, but if all cattle in Northern Ireland were to extend grazing by 2 weeks, I think it would give us a 3 to 4% reduction in total agricultural ammonia emissions, and that's quite significant. In fact, it sounds like not a lot, but it's a significant reduction.
Yeah, no, it really is. I agree, John. So, look, Alistair, I'll pass back to you. There's lots of interesting questions as well, but we will get back to those folks in due course and in writing.
Yeah, thanks, Paddy. Just to reiterate that any of the questions that we don't get time to cover in the seminar, we will reply to via email. So each of them will be responded to, if not today, in the near future. So thanks, John, indeed, for a very comprehensive paper. And having looked at the impact of ammonia reduction measures on emissions at farm level, we're going to now look on the economics of reducing ammonia emissions in Northern Ireland in a presentation from Erin Sherry. And welcome, Erin, to the webinar this afternoon. Erin leads the Regional Economics and Sustainability team within afbi's Economics Research branch. Her team investigates both the economic and environmental sustainability of UK agriculture. And Erin, we're looking forward to your paper on the economics of reducing ammonia emissions in Northern Ireland. Thanks, Erin.
Thank you. Good afternoon. I'm very happy to be presenting an economic analysis that was led by my colleague here in afbi, Aurelia Samuel. This work was a collaborative effort involving economists as well as other scientists across afbi and our partner organizations. While John's presentation takes an in-depth look at what may be technically possible in terms of reducing ammonia on a given farm, this analysis estimates what could potentially be reduced across the whole agricultural sector. So this is more about looking at sector-wide costs associated with a range of ammonia reduction levels rather than achieving one particular target. Going on to the next slide, please. I will provide some information about the general approach. In this collaborative approach, economists calculated estimates of the additional cost of adopting a measure that is expected to reduce ammonia without impacting the level of production. These cost estimates are based on the expected difference in variable costs, such as changes in feed or bedding requirements, as well as the estimated additional fixed cost, such as investment in new equipment, associated financing, and the maintenance of that equipment. Capital costs were converted into a yearly cost estimate by spreading the cost over the expected lifetime of the investment. In some cases, costs were spread over animal places per year. To do this, costs were divided by the number of livestock units. Input from agricultural scientists and policymakers was incorporated to establish the representative farm scale used to estimate the per animal place cost. Colleagues across afbi and Indera also provided valuable insight as to what percentage of farms could realistically adopt the measure within a 5 to 10 year implementation horizon. Environmental scientists contributed to the ammonia reduction potential of each measure, and this was based on the results of scientific research carried out at afbi, as well as the Tier 3 certified relationships that are used within the NARCES model. John spoke a bit about this in the question section, and there's also more information on this in the first webinar in the series that is now available as a recording. The NARCES model was then used to determine the marginal benefit of layering each of the measures on top of one another. This gives us an estimate for the sector as a whole and the associated costs of reaching different levels of ammonia reduction. Going on to the next slide, please. I will outline the remaining presentation that highlights the results. So I'll start off with listing the measures that were identified and that are costed and modeled, along with the assumed uptake rate used to estimate the aggregate figures. Then I'll present the costs calculated for each of the ammonia reduction measures, then the amount of ammonia that could be reduced in the sector for each measure if it was adopted by the assumed proportion or uptake rate. Then I'll explain a bit about marginal abatement cost curves, which is the modeling approach. And then I'll present the marginal abatement cost curve for ammonia in Northern Ireland. Then we're going to focus in on the 5 most cost-effective measures, and finally a summary and some potential ways forward for the research. Going on to the next slide, please. I'll take us through the ammonia reduction measures and the assumed uptake rates. So many of these have already been covered in detail in John's presentation looking at the farm level ammonia reduction. So what's important here is a reasonable rate of adoption across the sector, or uptake rate was determined through collaboration and discussion amongst the expert group of scientists, policymakers, and economists. We'll just talk through these briefly and the assumed uptake rates. So with the low protein diets, that's the reduction of protein in feed. And the assumption here is that 75% of these livestock populations are given the lower protein diet. Genetic improvement, these are selected traits for feed efficiency, and cattle is assumed to take this up 50%, pigs and poultry 75%. Extended cattle grazing, so this is the extension of grazing by on average 2 weeks, and this is assumed 100% uptake. Washing dairy collecting yards, this is assumed to apply to 15% of the dairy yards. Slat mats and cattle housing, this is assuming 30% and of dairy and 30% of beef cattle are moved onto slatted housing. And in the case of beef systems, we are assuming that a scraper will need to be purchased. So that has an impact on that per animal cost when we get to that stage. Pig and poultry housing, this is where ammonia abatement technology or practices are incorporated into housing for pigs and poultry. Covering above ground slurry stores, assume 30% will be covered. Slurry spreading, this is also assumed 100% uptake across the sector, but this is divided between trailing hose at 50% and trailing shoe at 50%. Then the use of protected urea and fertilizer, and this also is assumed that this would be applied 100%, so across the entire sector. A couple additional measures here were added in by the research scientists, and this is the acidification, which is a much smaller uptake rate, only 5% in pig and dairy houses and 10% in the field. So this is also looked at. So I think what's important to take from this slide is a sense of how some measures are assumed to be very widely adopted and others are not. So these charts, yes, thank you, next slide please. So these charts here will show us the estimated yearly cost associated with capital, which is in orange or yellow, or operating cost, which is represented in black. The costs are expressed as either pound per animal placed per year, in pounds per unit of slurry, or pounds per kilogram of N. You may notice one of these measures has a negative cost or a savings. This is extended grazing, and some have no cost, such as genetic improvement and low protein feed. In the case of grazing, this reflects a savings on variable costs due to reduced feed purchases. In the case of genetic improvement and low protein diets, the expert group determined that the farm level cost would be modeled at 0. This is because they're based on improving the overall productivity of the sector, and that means producing the same level of output with a lower level of inputs. Looking at the measures replacing urea with protected or stabilized urea, it's assumed that there will be an additional cost of 8 pence for each kilogram of N purchased. That's how that's read. In the case of low emission slurry spreading, the cost estimate is 61 pence per cubic meter of slurry for trailing hose, or 73 pence per cubic meter of slurry for trailing, for trailing shoe. So going on to the next slide, please. This chart shows us the potential sector level reduction of ammonia when each measure is used in isolation. And the number in parentheses is the assumed rate of uptake in the sector. So for example, and there was a question on this earlier, if grazing increased an average of 2 weeks across the whole sector, about 1,000 tons of ammonia would be abated or reduced. If 30% of dairy cows were moved to slat mats, around 250 tons would be abated. So going on to the next slide, please, we see how these input costs and ammonia reduction potential figures are combined to establish their marginal cost effectiveness. Now, the marginal abatement cost curve, or MACC for short, is a modeling tool that adds ammonia reducing options on top of one another. And it starts from the least cost per unit of ammonia abated to the highest cost. And the marginal benefit of adding additional options means that emissions can't be abated twice. So the benefits of this is the MACC can tell us how far we can get with low cost options. It can tell us where the big jumps in costs are. And it can tell us how much ammonia could be avoided overall in the sector if all the options we know of are used. So going to the next slide, please, we will break down how we can read or interpret a MACC. So each ammonia reduction measure will have its own rectangle. The wider the rectangle, the more ammonia is reduced by adopting that measure. The higher it is, the more expensive it will be. So going on to the next slide, please, we see that in some cases, a measure can have a negative cost or savings associated with adopting the change. And this is where the rectangle goes the opposite way, below the zero. This is usually linked to the fact that the measure enhances productivity or reduces the amount of inputs required to produce a certain level of outputs. As the MACC starts with the measure with the lowest standalone cost for each unit of ammonia abated or reduced, then moves on to the next lowest, and so on until the measure with the highest standalone cost per unit of ammonia is abated. This means that the model does not allow emissions to be abated twice. So instead, it takes into account that the marginal or additional emission reduction could be less than if a measure was taken up on its own. As we move further to the right along the curve, there's what we call a diminishing marginal return. It's getting more and more expensive to step up to the next level of ammonia reduction. This is in part because the measures on the right have a higher input cost to start with, and in part because some of the ammonia they may have abated has already been removed from the system. So there is an even smaller marginal benefit in terms of reduced ammonia at the aggregate level. So on to the next slide, please. When 13 ammonia reduction measures are layered in a MACC, we get an estimate of how much ammonia could be reduced in the sector. Given the assumptions about farm scale, uptake rates, and financial costs of implementing these measures, a 25% reduction requires $31 million per year. These costs are based on an implementation horizon of up to 10 years. Looking at the large purple rectangle, low emission slurry spreading, we can see that this is the widest rectangle. It's reducing ammonia by over 2,500 tons over the year, providing the largest reduction in ammonia of all the 13 measures. Low protein diets and genetic improvements have zero cost because of the productivity enhancing impacts of these measures. And we see clearly here that there is a steep jump in costs with very little additional ammonia reduction once we get to the right of that big purple triangle of the low emission slurry spreading. So going on to the next slide, please, we'll have a closer look at the first part of the MACC, or the 5 lowest cost measures. We find that sufficient uptake of the 5 measures can generate a 22% reduction for a cost of only $7 million. These include the extending cattle grazing by an average of 2 weeks, of lowering protein in feed, genetic improvement to livestock, replacing urea with protected or stabilized urea, and low emission slurry spreading, trailing shoe and trailing hose. Each of these will require a different amount of time to implement and face different challenges. However, compared with other measures, they have the potential to deliver a significant reduction in ammonia. Going on to the next slide, please, we can sum up and consider the future directions for the research. So here we have an estimate of a 22% reduction of ammonia across the agricultural sector for just under 7 million pounds per year. Reducing beyond that 22% becomes much more expensive for each unit of ammonia reduced. However, there is definitely potential to consider additional measures as technology and practices evolve. This is a sector-wide cost that has been calculated, but tools are needed to support farm-level decision-making. Interaction with other environmental pressures is not included. That's something else to be considered, as well as what practical strategies are to help with adopting these low-cost measures that have been identified. So with that, I'll say thank you very much.
Okay.
Thank you very much indeed, Erin, and apologies. Paddy, it's taken me a while just to unmute there and find the video button. But again, Paddy, and thanks, Erin, for, again, a very comprehensive paper. And Paddy, could you start to take us through the questions that are coming through?
Yeah, I suppose the first one, Aaron, is in around the assumptions relating to protected urea, and I suppose the basis of the question is why not just get farmers to use CAN instead? Focusing on protected urea could see farmers move from CAN to protected urea, and thus increasing ammonia emissions.
So maybe I'll widen that question out, Paddy, to bring in Tom and John in that, because of course we're looking at ammonia emissions today, but in the context also of wider environmental issues such as greenhouse gas emissions, which are consequences of that. And maybe, Paddy, that's one that specific to fertilizer that Tom Misselbrook would pick up in the first instance.
Yeah, okay. Thanks, Alistair. I can say a few words to that. So you're absolutely right. We have to look at the trade-offs between ammonia and greenhouse gas emissions. I mean, we need to do that for all measures, of course, but as you're right, switching between fertilizer types has some implications there. I think the other issue is that farmers may have their own reasons for using urea and want to continue to use urea. So, the best thing we can do then is to ensure that if they're using urea is stabilized urea. As to whether there would be a swing from CAN towards protected urea, I guess is questionable, but others probably know more about that than I do.
Thanks, Tom, and back to you, Paddy, for the questions.
Yes, so there's another question that's come in around low emission slurry spreading. It's probably going to be more for policy, but I suppose it's just a question about could there be a grant system introduced for farmers adjacent to protected nature reserves to allow them to move to trailing shoe systems. I suppose the first thing to state is that there have been a number of grant schemes. Certainly from the MACC scheme under the previous rural development programme, and then in the most recent trailing shoe and trailing hose systems have been part of the farm business investment scheme. So there certainly has been a number of those types of initiatives, and certainly the idea of looking specifically at areas of some people in adjacent to particular areas is something that can be considered. So that's from a policy perspective. I'm not sure if anybody else has anything that they'd like to add on that. Okay. Okay. So, and then the next, again, is probably a policy type question. The 22% reduction costing 7 million, is the reduction enough? I suppose that's maybe something that we'll also address tomorrow in some of our presentations.
On Friday's seminar.
Sorry, Friday. Sorry.
We'll be looking at the follow through for these reductions on atmospheric ammonia concentrations across Northern Ireland and at sensitive habitats. So that will be picked up on Friday's seminar itself.
Yeah. Okay. Yeah. And then I suppose there's another one here, Aaron, in relation to the low emission slurry spreading scenario. And would the cost be reduced if it was assumed that this was undertaken by contractors versus farmers buying their own machinery? And I know that's something you looked at in the wider work. You looked at both types of scenario.
Yes. So in this analysis, the cost is based on contractor costs. So it's based on the marginal difference between contracting to have it spread by a low emission means as opposed to by splash plate. It's that marginal difference, estimated marginal difference in the contractor cost. Now, this is something that is going to change over time in response to market forces. So it is something that would probably need to be looked at again, just to revise that and get something maybe more up to date. The other issue is because it's not so widespread within Northern Ireland, a lot of our data needed to come from other places, such as the Netherlands, where there are contractors routinely applying this technology. So there's definitely room to refine that down and maybe just have a look in a bit more detail about where that would be now.
Barry, there's a theme coming through in some of the questions that Erin might be wanting to pick up on. Some of the measures are win-win. What are the barriers to uptake, and how do you achieve quick and widespread adoption?
Well, I think in that case, the challenge first is understanding the problem. So why or isn't this being done in different contexts? For example, with the extended grazing, it's a matter of providing farmers maybe with more information on why it's beneficial and how it could be incorporated into their existing production systems. And beyond that, there may be other strategies to encourage uptake. And there's a body of research on behavior change and how that can be spread within a farming community. So I think that will be an important thing to look at.
Yeah, and I suppose, Alistair, from a policy perspective, it's also important to point out that in terms of getting the behavioural change, that the proposals that will be made in the draft strategy, which we hope to consult on, will look specifically at this issue. That we have the scientific evidence base here, and then I suppose the next step is how that translates into proposals for ammonia reduction.
Thanks, Paddy. And we have 5 minutes now when we can broaden out the Q&As and cover back to John's presentation as well, if there are areas, Paddy, that we haven't covered. So I'll just pass over to you, Paddy, just to create the next question.
Yeah, I suppose one question that's come through is around the extended cattle grazing period and the assumption that that's 100%, and I suppose the very valid point being made that, look, in not all areas will that be possible. My understanding, Aaron, but perhaps you can confirm, is that the 14 days is seen as an average, and that it's adoption as an average over the entire industry.
Yes, that would be an average across the sector. So it wouldn't be necessarily on every single farm. It was extended by 2 weeks. And some it might not be extended at all, and at others it might be extended more than 2 weeks. And I think a way to think about that, if you think about the MACC, the shape of the MACC, so that rectangle, that represents the low emission, or the extended grazing, if you reduce the uptake rate, that's going to shorten the width of that rectangle a little bit. So that's one way to think about that. So if you say, okay, well, only 50%, you can sort of picture that at half its width, if you see my point, to sort of get a sense of the impact.
Yeah, no, thank you, Aaron. John McElroy, if I could maybe bring you in. There was just there was a lot of questions I suppose came in on yours as well. Just maybe to throw back to one of them, as Alistair had suggested about is it possible for the types of farm level modelling that you have done to be available to farmers so they could input their own data and give them an idea of their own ammonia emissions and the impact of different mitigations that may have planned? So basically the farm carbon calculator for ammonia. I think that's probably something that isn't currently available, but that there certainly as a scientist you may see a benefit in.
Yeah, absolutely, Paddy. That's a really good question, and we do have the intention to develop a decision support tool for farmers on ammonia in a similar way that I presented farm scale emission reductions with sort of set parameters. The option will be there for farmers in a calculator type form to input parameters from their farm, how many animals they have, what type of housing systems they have, how they store their slurry, how they spread their slurry to estimate emissions from their farming system. And likewise with the scenarios I presented today, to start to input and play around with some mitigation strategies which have proven scientific research behind them in terms of ammonia reduction potential, and apply those to their farming enterprise to determine the potential reductions in ammonia that are achievable on the farm. So yes, absolutely. I think that's it's an important step to develop that decision support tool for farmers.
Yeah, and I suppose another theme, Alistair, that's come up in the questions, and we've dealt with it a little in relation to stabilised urea, but there's a more general question around the farm measures that have been looked at in both John and indeed Aaron's presentation. How are some of those potentially antagonistic, or how do they link to other environmental dimensions, for example, greenhouse gas, water quality, biodiversity? And I suppose it's an interesting theme. I mean, one of the low emission slurry spreading, I suppose, is a classic example of something that works really well across those various metrics.
Yeah, maybe you want to pick up on that, John. Obviously, low emissions also has a beneficial effect from a P loss to waterways perspective, and maybe from a GHG perspective. Maybe Tom wants to come in there.
Yes, Alistair. I mean, we've already touched on the urea can issue and the potential to potentially increase greenhouse gas emissions while lowering ammonia with a move potentially from urea to can. But there are lots of other examples. And it's something that we in our research have to consider fundamentally in terms of pollution swapping. So another issue maybe that hasn't been raised with, for example, slurry acidification is the potential for the mitigation of P, because there is evidence that acidified slurry can provide up to a 40% increase in plant available phosphorus. And with our soil conditions and the phosphorus status of soils in Northern Ireland, there could be a risk of soil P mobilisation. So that's something I think we need to look at. Other techniques, for example, maybe that I haven't touched on in the presentations, but which is equally valid, for example, slurry aeration, and that's a practice which has seen increasing uptake across Northern Ireland. And there is good evidence to suggest that slurry aeration has a significant reduction in greenhouse gases, particularly methane, but also in, for example, odours and also hydrogen sulfide. Now, unfortunately, for ammonia, the evidence is much less clear. In fact, it's contradictory, and I think we need to carry out some research into that. But in theory, there is high potential, and some of the studies have shown this, that aeration would increase ammonia emissions. So there is, when you look at all these strategies, it's hard to find a silver bullet. But we need to consider the wider pollution swapping ramifications of these reduction strategies for ammonia.
Okay, thanks, John, and I appreciate we're getting very sort of towards the close to the end, but there's just one question that's come in that I would just like to throw out for comment, and it's around slurry injection, and there's a question of whether there should be more focus on that, given that there's it has the potential to reduce ammonia by more than either trailing shoe or dribble bar. Now I know it's something that has its challenges, John, but also, very much has a lot of potential. There's certainly a reward there too in terms of ammonia reduction.
Absolutely, Paddy, and absolutely. But just because we haven't touched that in these scenarios, absolutely wouldn't rule it out in Northern Ireland. Under certain conditions in certain areas, there are obviously topographic and geographic limitations here because of these systems tend to be suited, to flat fields, sandy fields in particular, maybe more than what our kind of stony drumlin type landscape that we have in Northern Ireland. It may not be totally suitable. But there may be an opportunity there for agri-tech companies to try to apply those types of, or try to adapt those types of systems for use in Northern Ireland under our kind of environmental conditions here. The reductions are well known.
Thank you, John, and thank you, Paddy, for collating those questions. We've just hit the end of our seminar here, and it just remains for me to thank again Erin and John for their presentations this afternoon. To all the panel members for joining us on the webinar, and we look forward to joining with you again at lunchtime on Friday when Uli Dragosits and Tom Isselbrook, who are on the panel here, along with John, will be focusing on the outputs from really extensive monitoring of atmospheric ammonia concentrations across Northern Ireland, which have been undertaken at farm, habitat and regional level. And we look forward very much to Friday's seminar, which follows on naturally from the work that's been presented here today. And finally, could I just thank everyone who's joined us on the webinar today and for their active participation in the Q&A session. Have a good afternoon, everyone. Thank you.